Avely, I'm a program manager at Microsoft, and I work a lot with Microsoft research in big data, large-scale computing, and I want to talk to you about some of the developments we've made over the past year or so as we've looked to really embrace the Hadoop ecosystem and other types of big data workloads to support research throughout the company. So there's been so many talks already today, and we're all here because we know the importance of big data. It's a critical tool for Microsoft's business, and it's a way to deliver transformative new capabilities to our customers. So this isn't anything new, but what is kind of interesting and what you may not know is sort of the historical context around Microsoft research. And sadly to say, the first thing I'm going to talk about is sort of the shame on us. If we look back even as far ago as 2 years, many undergrads had better big data capabilities than what Microsoft research had. Sure, we have access to the whole back end behind the Bing ecosystem, but that's not Hadoop. That's not a open standard type of environment for doing big data workloads. And we were really seeing that where researchers were having to build systems underneath their desk. There was not any standardized way of accessing data other than through what we call Cosmos. And so over the past 2 years, we really turned the course of our ship. We took a new direction to really embrace the whole big data Hadoop type of ecosystem and think about a way to better support our researchers. And so this talk is about what we did throughout that transformative journey and where we are today, everything from compliance, policy, data tools, all that kind of stuff, just to share where our researchers are going. So we created a project internally. It's called Grand Central Data. We took the name from New York's Grand Central Station. All the trains come to Grand Central Station, so all of our research data would come to Grand Central Data, having a sort of a one-stop shop for data processing tools, data ecosystem, data libraries for our researchers. So our vision for the project is there's so many different research areas driven by data. Data comes in from very different forms, different sources, and we needed some kind of standardized data storage and data processing for our community. And what was happening was research groups they have these different data sets, but they weren't sharing. So we had multiple copies of genomics data, image data, Twitter, all that kind of stuff, and you had researchers almost working and not knowing what the other team was doing. And so having this kind of resource and having all built around our research data, both internal and external research data, thinking about data sharing, the research need, how we adapt to change, how we're flexible. Microsoft research isn't huge, and it's really strengthened by its external connections. And it's really hard to work on top of a technology that's Microsoft internal, and that's what that's what was happening with the Bing engine underneath before. So by building on top of Hadoop, it gives our own researchers a way of collaborating and contributing more freely to the big data community at large. And I'll be talking at the end about some of these very examples that have been built on top of Hadoop that people can download for free and just use. They're out there in GitHub that have come from Microsoft research based on projects like this. And so the whole idea, this was our motivation behind creating Grand Central Data. We had some guiding principles. There are challenges that many data-driven and data-centric organizations have. Everything from security and compliance. You're dealing with genomics data, you're dealing with data that people have trusted you with, whether it be Twitter, Facebook, Foursquare, what have you. You have to make sure that you have a good security and compliance ethical type of story that goes with that. Worldwide access, MSR, Microsoft Research is not just in Redmond. We have locations and labs worldwide. And so our facilities might be located in Redmond, but how do we serve up data to our labs in Beijing, in Bangalore, New York, Boston, Cambridge, UK, all over the world? What kind of tools can we use? The other big thing was having a place that we can put the data from our partnerships within teams of Microsoft. As a research organization, it's hard for us to be parachuted into the different build environments and production environments where many of this different types of data comes from. So having a centralized data place that's controlled by the researchers that our production teams know is secure gives us a great spot for housing all of this data. And it's all driven by researcher needs. So the tools that are being driven, that's one of the reasons why the whole Hadoop ecosystem was pushed. Many researchers are used to building on top of Hadoop. A fantastic example is using Elephant Bird for the Twitter ecosystem. You can't go just plug that in to any off-the-shelf system. You need that Hadoop ecosystem to be able to leverage those economies of scale and have those community contributions. Our goals: so centralized, compliant, curated data storage facilities, multi-purpose data processing architecture. It's a mix of different types of tools and hardware, flexibility with software, and a user community supported through outreach and training. So with all of these goals in mind, we have this notion of Grand Central Data with centralized data management, research, innovation, and support, tools and hardware, partnerships, privacy and security, all driven with community and outreach. So now that I've set the stage, I want to go another layer deeper and start to talk about some of the tools and the architecture that we've been building with. The first type of one I'm going to talk about is what we call our sandbox, and as we have large-scale GPU-type systems. Many different types of data-driven workloads, be it deep neural net classifiers, need GPU technology to drive additional insight out of the data. So we have our standardized data ecosystem, our data lake, if you will, in the middle, and these are all the different types of hardware. The GPU system is a large-scale GPU ecosystem, and some of the things that it's driven has been, for example, the Skype translator. All of the processing for the creation of the voice models was driven using this ecosystem. Also, we have a notion of what's called our sandbox. So these are high-end prototype type of machines that people can reserve on an individual basis and use it as you would an administrator plugged into our data, our complete data access. So production GPUs, sandbox machines, that's one of the areas where we give some of the flexibility. Another area is looking at our Hadoop ecosystem. So we have the largest. I don't know whether this is a bragging thing or if it shows that the lack of adoption of Hadoop on Windows, but we have the largest on-premise Hadoop for Windows cluster there is out there today. And it's been really nice to see how that's been able to drive some really innovative workloads on top of Hadoop. Examples include work that's been done around ImageNet, Minisort, benchmarks. There's quite a fantastic machine learning package that came out of our New York lab called the Vopal Wabbit, which is all built on top of Hadoop. It can be run on Hadoop on Windows or Hadoop on Linux, and it's open source, it's freely available. But by having that kind of Hadoop ecosystem and the same Apache-based Hadoop ecosystem on Azure, it allowed researchers to, in very fast time, prototype and develop on our on-premise resources, and then share those workloads seamlessly. There's no recompile, there's no rebuilding. They just migrated it very easily onto Windows Azure with HD Insight, and it could move seamlessly. And that was a great example. One example I'll be talking about later is called SNAP, which is a genomic sequencer that came out of Microsoft Research, that all the on-premise work for that development was done on our on-premise Hadoop cluster, and then it was made available and shared on top of Windows Azure. If you look for SNAP, it's out of Berkeley. Another example, I've got our sandbox again, because that's kind of a prototype system where you can play, you can have the sort of free access to the machines, but we also wanted to leverage the big compute capabilities. And so there are some aspects where you can use Yarn to drive MPI and OpenMP workloads. It's kind of a fuzzy area where we're pushing some of the boundaries as being compared with traditional job management and job schedulers. But another big driving factor for our workloads is the high-performance computing workloads, which can be done on-premise and on top of Azure. But by having that same common data pipeline here enables much more faster time to innovation and data sharing and data productivity. The other part that I can't forget is the Bing backend. It's called Cosmos. And so part of our pipeline is having something that works well, containing everything within HDFS, but then can talk and move that data around from the Bing backend. So here's examples of the different types of data we have in our research catalog. We've got botnet data from the Microsoft Digital Crimes Unit, NOAA weather data, ImageNet, CFAR10, MNIST, that's your handwriting samples, Cortana audio data for tagging with emotion, Skype translator, Skype call data, Facebook, Twitter, Foursquare, Facebook, and other data sets that have come out of Microsoft Research as well as parts of the 1000 Genomics project. What we loved about the Hadoop ecosystem and why we chose HDFS as our main file system was the flexibility it offers for all of these data type of workloads and the breadth of processing that we're able to get through Yarn and the different types of plugins for different types of workloads. So this is a sort of an overall picture of our large-scale ecosystem. We've got the Bing backend here. That's one of our main data providers. We also have, there could have been another blob there that said external sources or production teams, and it comes into our main data ecosystem. The hardest problem for us has been that sort of HDFS is good, but it's not there yet for all of our needs. And so how do we balance between a traditional big compute, high-performance computing type of ecosystem, as well as something that's being driven through big data? A lot of these things, these problems are the same. If you look at what's happening with big data and high-performance computing, we're kind of converging. It used to be, did you bring your data to your compute, or did you bring your compute to your data? We're getting close enough where these are really converging, and it's a hard problem to solve from an architectural point of view. And so we've used the Windows HPC scheduler and Windows HPC server as part of our ecosystem, and then we've used the Hadoop on-premise ecosystem, and we've really tried to balance that relationship between the two. We can manage our workloads through the Windows HPC scheduler and schedule things out on top of our Hadoop machines, as well as we can use the Hadoop schedulers and manage our workloads that way. Some of the tricky parts, especially being on Windows, has been things around libHDFS support, how we programmatically access our data in HDFS. You're getting into just the stability, examples of Cygwin, compatibility, all those kind of things. It makes some of our workload migration very challenging. The nice thing, though, is this line here represents the division between on-premise and into the cloud. Here, it's already built in. You can take the Windows high-performance computing scheduler and say, give me X number of Azure nodes, and just seamlessly migrate my work onto Azure, provided the data is already there. That's the tricky part. The nice thing, though, about the HDFS going to HDI is that your code just works. So we have burst strategies in both our Hadoop path and our traditional compute path. What I'd like to see someday is all of this combined. So using Yarn to perhaps talk to different kinds of schedulers, whether it be LSF, PBS Pro, Grid Engine, all those kinds of things. Could you use Yarn as your centralized orchestration? That's one of the problems that we're tackling in MSR, trying to figure out what our vNext is going to be around a job scheduling tool. Similarly, how do we interact better with the Bing ecosystem? Is there a way to automatically submit jobs from here that could go and run with the data on Bing and back and forth? Having that kind of technology migration and workflow migration across all of these platforms is something we haven't figured out yet. This is still our V1, and we're looking ahead. Important for us, just to recap, for this part is the workflow from your traditional HPC to the Hadoop ecosystems, as well as a burst strategy, so that you can easily migrate to the cloud, whether it be for traditional HPC applications or for Hadoop-based ecosystem. So we've talked about our goals, our vision, and then we have our data ecosystem, our architecture, but we were missing a real key part here, and that's all of the data management. This is the hardest problem of all. So we have all of these different kinds of data. You've got everything has different requirements. The requirements for Twitter and Facebook are very different than some of the publicly available sets through Microsoft Research. How are you managing those user profiles, granularity, access? It makes me feel like I'm in a hazardous chemicals lab. The path from combining different data results, if I pick one path, it can be safe products all the way along. If I go through a different direction, I could combine two different types of data, and it could create something that's very, almost explosive-like in terms of the privacy, security, and ethical responsibilities that are associated with it. So the trio that we're trying to figure out is compliance, security, and ethics. The software stack isn't there yet to solve it all for us. It's a real mix of data management tools and policy. And how can we enforce policy, create policy that then gives us the best use of our data management technology. This is one area that I'm really excited to see growing within the Hadoop community, things like Ranger, Apache Ranger, the different security models. I know that there's integration with Active Directory, looking for those kinds of things to help strengthen what you can do from a security and monitoring point of view, but you still have policy, how you actually control access and grant people rights. Auditing is very tricky. I'm doing work now with some genomics companies and genomics partners, so the whole notion of health compliance and auditing and encryption, all of this kind of stuff is coming up. Even if it's used with some internal facility like this at Microsoft Research, you still have those problems to solve. So when I think about the security, compliance, and ethics, I can look at security. We have ways of enforcing policy and procedure. One of the things we do at MSR is we have certain sets of standardized training that you cannot get access to our systems unless you take that. It's recorded, it's monitored, and you're reminded every couple of months saying, hey, your training's out of date, you got to retake it. It will disable your accounts if you do not take this training, kind of thing. So that's one way that we can help enforce policy and procedure. You have sort of watchdogs where you can watch network traffic going on and off the machines, utilization, that kind of stuff. Standardization across the common platform, well, we're getting there. We're using Hadoop, HDFS, and Yarn as our core ecosystem, pushing the boundaries a bit with some of the GPU hardware. Doesn't always talk nicely through Yarn, how we can leverage those GPU resources a little bit better through the scheduler and manager. And so we're still relying on things that we used before in the Windows HPC scheduler, and where we have a good story between how we go from on-premise into the cloud really helps, but there's still gaps. And those gaps are what we start to identify through with technology. Compliance. So one of the things that I had to do in my role when I was managing all of these data sets was there were monthly meetings with legal and ethics. And so we would actually manage proposals. People would write in and say, I want to use this data set. We'd have to review this and have the whole paper audit trail. That took a lot of human time. It would be nice to have some kind of a technology solution to help with that. Ethics. So the ethical use of the data. How can you make sure that someone is actually using the data and the facilities in the way they said they would? As an example, we had somebody that was doing, an intern that came in and was doing Bitcoin mining on our GPU systems. Okay, that's not what they signed up to use the systems for. That, again, took people to be diligent and monitor the types of workloads that were happening, but finding automated ways to have those watchdogs is super important as you start to work through different data sets and combine different pieces of data. So, but looking across the Yarn and HDFS, all of this kind of stack, we get a whole pile of flexibility and tools that help us doing the security, compliance, and ethics by having the flexibility for our workflows. And that's been the big selling point for us as to why we've embraced Hadoop as one of our core pillars for Microsoft Research's big data ecosystem. So now on to some fun examples. So I've got 5 of them here. Skype Translator, F#, Naiad, Snap, and Azure ML. I'm going to start with Naiad. And if you haven't looked up Naiad in GitHub, I would encourage you to. It's quite a neat way of doing sort of graph-like analysis on data. It just works, whether it be on Azure HD Insight or on-premise, any on-premise Hadoop offering. It gives you a way of creating graphs for processing data. It's written in .NET, and it's got a lot of really neat built-in primitives and things that you can use to process that data in very small amounts of code. I was really surprised what I could do with 5 to 10 lines of code and streaming in from data pipelines, and I had a graph of what I wanted how I wanted to compute things and process my data. There were 2 main models for working with Naiad. One is you create a graph, sort of an ecosystem where the data comes in and it processes things based on the graph, and that graph remains stagnant. And it's there just saying, hey, I'm hungry, give me as much data as you want, I will keep processing it. But every time the data comes through, it treats that as an epoch, and it only has a notion of 1 epoch at a time. So it's that time slice that it comes through. It doesn't know what it came before, it doesn't know what is going to come after. There's another model where you can actually set up a graph that understands the historical context. So over time, it tells you how that data has changed and gives you those relationships. Anyhow, that's one thing that, because of what we did, and by having this on-premise Hadoop ecosystem, it accelerated the time to innovation with Naiad. One fantastic example that people have had, and it's checked in GitHub, is they were taking all of Shakespeare's work and streaming through a graph every line of every play. And it was just mash up all of Shakespeare, shove it through, and it started reading it in like a big fire hose. And it looked at a 30-second window for time as to what the lines of the plays were coming through. And in real time, it built a relational graph showing you which characters were talking to each other. And so it started to do clustering and show you had basically clusters in real time based on the different plays, because it figured out who was talking to who. It was a little tricky when it would say somebody speaks to all, and then you had one big blob, but very quickly after that it would break back out into the subgroups for the different plays. So that was a really neat example, and it runs on any Hadoop distro you have. Skype Translator. So who here has seen the demos or heard about the work that Skype's Translator is happening? So it's a way of Skype that allows you to speak in your native tongue and have it translated to other languages automatically in real time. The amount of training for the voice models, voice recognition is tremendous. Sort of the minimum bar is 3,300 hours with a 160 million parameter deep neural net. Something that took before 60 days on CPU-based technology. It's now down to 20 hours to process a whole language on using GPUs. There was a fantastic paper that came out, Interspeech, late 2014, talked all about the deep neural net training the models. It was all done on our Grand Central Data ecosystem, having that flexibility for the research models. F#, anybody heard of the F# programming language? So one of the things, it's a functional language, and that's type-driven. A fantastic example of F# is there's something called a type provider, where it will generate types on the fly as you're using certain instances or certain ecosystems. A type provider, one of my favorites, it plugs into the Satori or Bing Knowledge Graph backend. So I can go along and I say, I want something that's a type chemical. And then I can put a dot, and it goes and talks to the Satori graph, and it pulls back all of the then associated properties for chemicals. And just like when you're programming in .NET, You can type in string, dot, and then it tells you all the operations you can do after this. It can generate those types on the fly by talking with your Hadoop file system using HBase. It can talk to Freebase, different data providers, different structured data. That's something that, again, was developed significantly using our on-premise Hadoop ecosystem, and it works super well. It doesn't have to be with Hadoop, but now with the HBase plugins, you can take your unstructured data, create a meta-type scheme for it, and make it programmatically accessible through F#. A really neat innovation story. If you go to tryfsharp.org, there's a bunch of code samples and things that you can download. It's pretty neat. SNAP. So that's a scalable nucleotide alignment program. That was a joint effort by the eScience group from Microsoft Research and Berkeley. And so if you saw Ranga's keynote today, he talked about genomic processing in Azure and things. That group was part of that effort. What I love the story is they had a traditional HPC workload, so running through a Windows Hadoop scheduler, but because of the flexibility with Hadoop and the way technology was changing, it made it and because we had this ecosystem on premise, we were able to accelerate that program, that development of that code, and they converted everything to use Hadoop, which made it a lot easier when the time came to investigate using Spark. It was already there. They could just build on top of it. And by having on-premise Hadoop that was built in the same way as cloud-based Hadoop, HDI, it made that migration and the sharing of the information very seamless. So that was another nice story, just to see how it progressed from the cluster into the cloud, into the open source. And that just made me, it was really neat. Final example I'm going to talk about is Azure ML. It's a machine learning service that's available on top of Windows Azure. A lot of the development behind the learning models was done on Grand Central data. And because of the flexibility of the code, it runs through Yarn, it talks through to HDFS. It can be done using our GPU system, but it can also be done using our CPU-based system. Again, talking to those standardized data sets at the back end. Just another nice story, as we would have had to do a whole pile of engineering plumbing if it weren't for HDI, or if it weren't for Hadoop. So that's concluding my talk for today, and we've got about 10 minutes left in the session. So I did that purposely because I wanted to make some time for Q&A. I mean, I've given you a snapshot over what we've done. I'm sure many people are facing similar challenges in their own big data ecosystems, and I figured it would be a good chance to share, put me on the hot spot, or whatever you want to call it, with asking some questions. So does anybody have any questions or interests in anything that I've talked about today? Yes?
Could you elaborate a bit more? You talked about the HPC crowd and the Hadoop crowd.
Yes.
If I think about HPC, typically you have storage and processing who are separated.
Yes.
And Hadoop has typically been joined. Now we see these cloud systems, Azure, Amazon, object storage. What's your take on that?
Yeah, I can put back to that slide I hear. Right, so I got that whole blend between cloud and so my thoughts are in terms of the sort of the connection and having the close compute to the storage. I guess with a cloud provider, you're trying to abstract that away. It shouldn't really matter where you're running your CPU and you have your data. Having them co-located is great for performance, but if there's other ways that you can satisfy those performance requirements, then that's great. HDFS provided a fantastic API to plug into that distributed file system, and it was a great place to start. I think cloud providers, if they can choose to implement an HDFS file system on the cloud, or they could sit there and make a shim layer, make it so all the APIs just work. However, if the performance isn't any good, people aren't going to use it. So that's the hard part, is making it performant. And do you get into caching strategies? Do you get into geo-replication, copying? I don't know if they have a booth here, but I absolutely thought I went and saw a demo by WANDisco. Some of their stuff was absolutely fantastic. It was distributed HDFS across multiple cloud sites, and you could issue one command, and it checked for locking on files. It treated the distributed HDFS as one single HDFS, and you can put where the replications are. So that was a really neat approach, and I think stuff like that will help with getting that better performance and distribution across the cloud as we move from on-premise into the cloud. The HPC workloads, though, that's still I think that has more flexibility when it comes to Hadoop, because if you look at some of the traditional HPC workloads, whether it be a parametric sweep or what you might call embarrassingly parallel, or maybe something like a large-scale, large memory type of workload, sometimes the workload only needs a very small amount of data, and then it's generating the data, and it needs something to put it into. So having a very fast file system that's distributed could help, right? And so, yeah, you're spot on. We're at that real convergence, I think, between the HPC and the big data types. Pardon?
I completely agree.
Thank you. Yes. Oh.
So, can you tell me about something about how dynamic? Can you tell me something about how dynamic some of the data sets are that you work with? Are they just in there once and that's it, and that's what you
Yes.
use?
Okay. So that's a fantastic question. How active and how dynamic the data sets are. We have a few different requirements in that aspect. One is compliance. As an example, some of the data sets we use from Bing, we're bound by what's inside of the user agreement for people that use the search engine in different countries as to where that data may be collected from. And that requires us to be very diligent in how we monitor and how long we can keep that data. For example, some of the data we have can only be kept 18 months. So if we're taking an 18-month snapshot, we typically go back 15 months and then use it for 3 months and then get rid of it and refresh it. So we make sure we have some of the data we use is never older than 18 months, because we'd be in violation if we kept it. Our Twitter data that we use, we have a year-long rolling window, because it's important to have the seasonal data. You want to get the whole year ecosystem. The Twitter data is roughly, what was the calculations again? I think it was 1.5 to 2 terabytes a day of uncompressed text. So it added up, right? And we chose to do it in we do a monthly update. Some of the other research groups that work with this are needing now streaming data, so they're wanting real-time updates. A really neat project is coming out of our Clues group, is they're trying to look for Twitter and asking questions. So if I get a cat, what is going to happen to me? Or what are the experiences that I'm going to maybe have in common with other cat owners versus what experiences would I have if I don't have a cat? Just as a cat was just a random example, but it's an interesting way of trying to learn from this different data. So yes, we have it all across the board. Some of the data we have was from a fixed point in time. Other points of data we're having to refresh reasonably often because of compliance and regulation issues, and then we have streaming data that's with the need.
So how do you securely get rid of data in this scenario?
So in this case, it's right now we're trusting that the file system is deleting when we have to. We're trusting our users to not go do recovery and try to scrape it and try to reverse engineer it. It's a limitation, but you have to trust your users. And that's why we have sort of the training, the monitoring and things to sort of show our users that we're watching. At the end of the day, we're all working for the same company. It's not like it's some open shop to who knows what. But yes, you're very right. There are things that need to be done better going forward or worked on in helping to improve technology. One of the fantastic examples is our agreement with Twitter. and we're very good about doing this. At any time, so we get the Twitter data from Bing. Bing has a license with Twitter. And so the Firehose comes in, it's managed here, we put it over, it's locked down. Only researchers that have approved proposals can use the Twitter data. It's refreshed at a known rate. But at any time, we have to be able to, a call could come from Bing and saying, right, you need to delete this portion of your Twitter data. And we have to be able to contact all of the researchers that have used that data, ensure that it's deleted from whatever stuff they've used, and then also deleted from wherever we're storing it. So yeah, right now there's a lot of manual kind of watchdog processing, but that's a very tricky area. Okay. Are there any, oh yes?
So regarding data governance, are you using Falcon or what are you using to make sure? Yeah, so regarding to data governance,
Yes.
are you using Falcon or what are you using to make sure some data got deleted in 1 month, other in 2 months? Because if you have 1 million, 2 million, 10 million files, 1 billion files,
Yes.
it's a huge work to know which file when to be deleted.
So we've started using Falcon, but we're also using other tools internally to Microsoft. One tool in particular is called RamWeb, which is it's a user rights and management tool. So I would apply for a data set, it would automatically give me a certain lifetime to be able to use that. It's not, and then when that expires, I'd have to go through the application and process again. So any push of a button, I can know who's approved, what their historical access has been. But yes, that's a real important piece. But yeah, we've really liked what has been coming with Falcon, and that's something we're incorporating into this initiative. One of the other hard problems is getting the data into a format that makes sense when we put it into HDFS. I feel like you have to be kind of almost like a data magician, if you will, figuring out the right packaging. Whether if it's text, what kind of compression are you using? If it's images, how are you using Avro? Are you structuring things in a certain way? How do the whole import process into HDFS is another really hard problem because of the variety of data that we have. Okay, I got time for one more question, if there's one more. Yes?
So you're handling tons and tons of data over several platforms, I see. Do you have a specific way you're handling the metadata about the data? Do you have something centralized that can give you a view of where the data is coming from, where it's going to, what's happening to it? Or is it something that you have to deploy depending on what you're working on?
So the metadata we've done it in 2 ways, and it's very, I'll say, basic at the moment. We have an internal wiki site that the data contributor describes all of the data, and you have a very detailed format of how the data is structured, what the columns are, things like that. And then we ask the researchers to share tools. So if somebody creates a JSON parser, JSON information about the data, that's put inside of HDFS in the file system where the data lives. It could be XML descriptors, so forth. So we try to balance it with sort of our community-based wiki where people can update it as the data changes and gets evolved, then having sort of open tools where if somebody makes something that makes the data more useful or can create something that, if you pull the data into Hive and you create a particular view of the data through Hive, then you can share that with other researchers. But still, we're trying to make it very community-driven, and so it can be grown that way. Okay. Well, that's everything. Thank you very much. Thank you.